So, in the last lecture we were looking at flow in a pipe, a cylindrical pipe in which in order to generate a flow you have to apply a pressure difference across the two ends of the pipe in order to compensate for the shear stress, the stress that is applied by the wall on the fluid in the direction opposite to flow due to fluid friction. And it is not just the wall shear stress, but you could also have stresses within the fluid. And I had defined for you two different distinct flow types in the flow through a pipe. One is the laminar flow, which is usually observed when the Reynolds number is less than about 2100, where the streamlines are nice and straight and smooth. There is no velocity in the direction perpendicular to the flow, and any cross stream mixing takes place due to viscous diffusion, due to friction, due to the viscosity. And at a Reynolds number of around 2100, there is a transition to what is called a turbulent flow. A turbulent flow is characterized by large fluctuations in the direction in all three directions within the flow. On average, if you average the entire velocity over time, you will find that the average flow velocity is only in one particular direction. So, the average flow velocity is only along the axis of the pipe. However, in both directions perpendicular to the axis, you do have instantaneous fluctuations in the velocity. These fluctuations are on average 0. So, there is no net motion perpendicular to the axis of the pipe. However, there are instantaneous fluctuations which take place. These are in the form of correlated parcels of fluid called eddies, and these transport momentum in the directions perpendicular to the flow. Because of this, the rate of momentum transfer across the flow is much higher in a turbulent flow due to turbulent eddies in comparison to a laminar flow where the transport is due to molecular diffusion or due to viscosity. For the laminar flow, the velocity profile is parabolic, and the wall shear stress has to scale depend only on the viscosity. It does not depend on the density, and based upon that the wall shear stress has to be proportional to, from dimensional analysis, the viscosity, the average velocity, and the pipe divided by the pipe diameter, which gives us a friction factor that goes as 1 over the Reynolds number. If the wall shear stress is proportional to the viscosity times the velocity divided by the diameter, the friction factor is proportional to 1 over the Reynolds number. You can actually calculate the value of the friction factor. We will do that later in the course, and you will see that the friction factor is equal to 16 by Reynolds number. After the transition takes place to a turbulent flow, the velocity is flatter, more plug-like at the center, and it has steeper gradients at the walls. In this case, as I said, at the center of the pipe, the transport of momentum is due to turbulent eddies. And the friction factor in this case is higher than what it is in a laminar flow. The friction factor depends upon the Reynolds number, of course, but it also depends upon what is called the pipe roughness. At the wall, if the pipe is not exactly smooth, you can generate little flow patterns close to the wall, which could increase the friction factor because these flow patterns are increasing the dissipation of energy, and therefore the friction factor depends on the wall roughness as well. For a completely smooth pipe, you get one particular value for the friction factor versus Reynolds number, and as the roughness increases you get slightly higher values. And I had also discussed the Colebrook equation for the fanning friction factor with you. This equation is an explicit equation for the average velocity if the pressure gradient is given. You cannot get the pressure gradient from the velocity because you can see that on the left and the right sides there is both the friction factor and the Reynolds number. Therefore, it is not an explicit equation for the friction factor, but it is an explicit equation for the flow velocity if the pressure gradient is known. So, this in short is the summary of the flow through a pipe. Okay. The next configuration that we will analyze is what is called the flow past a flat plate. Okay. In this configuration, we have a flat plate. Okay, of negligible projected area perpendicular to the flow, okay, past which we have a velocity Vfs, which is the free stream velocity far upstream of the plate. Okay. I will put a coordinate system here. X will be the direction along the plate, and in this case I will call Z as the perpendicular direction. Okay. And as the fluid goes past the plate, the streamlines of course have to go around the surface, but however the projected area of the plate is negligible. Okay. It's the thickness is very much smaller than the length of the plate, which we will call L. Okay. The thickness is much smaller than the length of the plate, which we will call L. Okay. So, so, therefore, there is no significant blockage of the fluid due to the plate. Okay. There is very little bending of the streamlines due to the presence of the plate. Okay. However, the velocity profile, because the plate is a solid surface, the mean velocity, the fluid velocity has to decrease to 0 at the surface. Okay. The fluid velocity has to decrease to 0 at the surface. Okay. And because of that, there is a disturbance to the velocity field, because there was no surface upstream for x less than 0. So, the velocity could be non-zero at the surface. For x greater than 0, the velocity has to decrease to 0 at the surface. Okay. And that is because of momentum diffusion to the surface. Okay. You know that the shear stress exerted is equivalent to a rate of transport of momentum. Okay. And that rate of transport of momentum occurs due to viscous effects. Okay. And because of this momentum transport, the velocity has to decrease to 0 at the surface, the velocity Vx. Far from the surface, the velocity is still Vfs. Okay. And in this case, it is not fully developed. Okay. When we had studied previously the pipe flow, we could make the assumption that the flow is fully developed, because there is no variation along the streamwise direction if you are sufficiently downstream of the inlet. Okay. If you are sufficiently far from the inlet, the velocity does not vary with downstream position. In this case, there is momentum diffusion from the surface. Okay. So, the velocity does vary with downstream position. Okay. The momentum that is diffusing from the surface is getting convected downstream due to the mean flow. Okay. In this case, it is a momentum in the negative x direction. Okay. Because flow is in the positive x direction, the plate exerts a flow, therefore, the flow exerts a force in the plus x direction on the surface, on the plate. The flow exerts a force in the plus x direction. The plate in turn exerts a force in the minus x direction on the flow, thereby retarding the flow and decreasing the velocity to 0 at the surface. So, upstream of the plate, there is no disturbance. At the leading edge or the upstream edge of the plate, okay, there is going to be the effect of flow, and as the momentum diffuses, right, there is going to be a region where the momentum diffusion from the plate retards the flow, and the thickness of that increases as x increases. Okay. This is what is called a boundary layer. Okay. It is often called by the symbol, okay, delta 0.99. Okay. Boundary layer thickness delta 0.99. Okay. Delta 0.99 because this is the y distance at which is the distance from the plate at which Vx is equal to 0.99 times V free stream. Okay. Okay, that is the definition of the boundary layer thickness. The thickness, the region within which the retardation of the flow due to the presence of the plate results in a decrease in the velocity. So, delta 0.99 is the distance at which the velocity is equal to 99% of its free stream velocity. Okay, that is the distance at which the velocity is equal to 99% of its free stream velocity, almost equal to the full free stream velocity. Okay. So, that is the boundary layer thickness. The velocity of course increases as you go downstream. Okay. Initially in the flow past a plate, the velocity will be laminar. Okay, you will have a laminar flow with nice smooth streamlines, and then there comes a particular location at which there is a transition. Okay, there comes a particular location at which there is a transition. Okay, and beyond this location, the flow becomes turbulent. Okay, you have turbulent eddies. Okay. So, as I said, this is a spatially developing flow. Okay. As momentum diffuses from the surface, the flow gets retarded to a larger and larger extent. Initially it is laminar, and then there comes a stage at which the flow becomes turbulent. Okay. So, this is the qualitative description of the flow past a flat plate. Okay. So, let us look at some dimensionless parameters. Okay. The Reynolds number is defined as rho V free stream times L by mu, okay, based upon the total length L. Okay, the rho V free stream into L by mu. Okay. In this case, the relevant length scale is the plate length L. Okay, because the thickness of the plate perpendicular to the flow is assumed to be negligible. Okay, so that is 0. So, the only relevant length scale is the plate length. Okay. In this case also the drag force due to the upstream edge is also negligible. Okay. And the drag force is primarily due to the shear stress that is exerted on the plate surface. Okay. The drag force exerted on the plate is primarily due to this wall shear stress, okay, tau W, that is exerted on the surface of the plate. Okay. So, that is the primary reason for the drag force. Okay. Therefore, the average stress note that as the velocity profile changes with downstream position, the stress on the surface will also change with downstream position. And since the velocity profile changes when it is a laminar or a turbulent flow, there will also be a change in the stress between a laminar and a turbulent flow. The average stress is defined as the drag force divided by L times W, okay, where W is the width perpendicular to the flow. The drag force is defined as the average stress is defined as the drag force divided by L times W. Okay. And what is called the skin friction coefficient is defined as this average stress by half rho V free stream square. Okay. So, that is the definition of the skin friction coefficient. and in this case the velocity scale is the free stream velocity. Okay. Now, since the velocity profile is changing with the downstream x coordinate, okay, since the velocity profile is changing with the downstream x coordinate, you can also define a local Reynolds number based upon the downstream distance x at a location, okay, which is equal to rho v free stream into x by mu. Okay, so that is the local Reynolds number based upon the free stream velocity. Okay. And this boundary layer thickness at a downstream location x, okay, as you can see this boundary layer thickness is increasing as you go downstream. Okay. This boundary layer thickness x, okay, at a given downstream location can be expressed in terms of the coordinate x, okay, as 4.99 root of mu x by rho v free stream. Okay. That is the correlation for the boundary layer thickness in a laminar flow. Okay. For a laminar flow, this is how the boundary layer thickness increases. As you go downstream, the boundary layer thickness increases proportional to x power half. Okay. For a turbulent flow, it has a different behavior, delta 0.99. For a turbulent flow, it is proportional to 0.37, okay, into root of mu by rho VFS into x power 4 whole power 1/5. Okay. Okay, for a turbulent flow. Okay. And you can also write down the ratio delta of 0.99 by x is equal to 4.99, okay, root of mu by rho VFS x, okay, is equal to 4.99 RE based upon x to the minus half. Okay. That is the expression for the boundary layer thickness for a laminar flow. And for a turbulent flow, delta of 0.99 is equal to 0.37 divided by x into mu by rho VFS x power 1/5, okay, is equal to 0.37 REx power minus 1/5. Okay. So, this is how the boundary layer thickness varies with downstream distance. Okay. And where does this transition takes place? Okay, this is laminar. Where you have nice smooth streamlines. This is turbulent, where you have eddies, okay, turbulent eddies. Where does this transition take place? This transition takes place, okay, at the location where, okay, transition Reynolds number Rex is equal to 5 into 10 power 5. Okay. 500,000 is the transition Reynolds number. Okay. And corresponding to these two skin friction coefficient, corresponding to these two boundary layer thicknesses, you can also the correlations for the skin friction coefficient are Cf is equal to 1.328 by Re per half, okay, for laminar, and this is equal to per 1/5 for a turbulent flow. Okay. So, those are the correlations for the skin friction coefficient in a laminar and a turbulent flow. Okay. So, this in short is the main characteristics of the flow past a flat plate. Okay. The Reynolds number itself is defined as Re is equal to rho VFS L by mu. Okay. The local Reynolds number at a given downstream position x is defined as rho VFS into x by mu. As you go downstream, there is momentum diffusion from the surface, and that momentum is being swept downwards due to the mean velocity. Okay. Note that the velocity far upstream of the surface is just the free stream velocity. So, that momentum is being swept downstream by the free stream velocity, and because of that the disturbance due to the plate, okay, the disturbance to the velocity field due to the presence of the plate is restricted to a thin region close to the surface called a boundary layer. This boundary layer thickness as a function of downstream distance goes as x power half for a laminar flow, okay, or the boundary layer thickness divided by x, that is the thickness divided by the downstream position goes as x power minus half, Reynolds number power minus half. For a turbulent flow, the expression for the boundary layer goes as Reynolds number power minus 1/5. So, that is a far more slowly decaying boundary layer. Okay. And you can see that 1/5 and half power are also present for the drag coefficient. We will see the reason for that later, but for the drag coefficient in a laminar flow it is 1.328 by Re power half. For a turbulent flow it is 0.074 by Re power 1/5. Those are the drag coefficient and the skin friction coefficient. This holds for, okay, this is for laminar flow, that is Re x less than 5 into 10 power 5, okay, or in this particular case it is just Re because, and this is valid for about Re less than about 10 power 7. Okay. So, those are the ranges of validity of these correlations. So, let us consider an example to see how we can calculate the drag coefficient and the skin friction coefficient in the flow past a flat plate for a real case. Okay. So, so this is x, this is z, this is the free stream velocity. Okay. So, I am considering the flow of air past a flat plate. Okay. Density is equal to 1.25 kg per meter cubed, and the viscosity of air is 1.8 into 10 power minus meter square kg per meter per second. Okay. And the free stream velocity VFS is equal to 2 meters per second. Okay. Okay, so, those are the density and the velocity. Okay. And what you are asked to find out is at what downstream distance does transition take place. Okay. what is boundary layer thickness. At transition. Okay, that is the second question. And what is the drag force? Okay. At what downstream distance? I will call this as LT does transition take place. What is the boundary layer thickness at transition, and the drag force for laminar and turbulent flows. Okay, that is, if the distance, if the length of the plate is L, what are the drag forces? If L is below the length at which transition takes place for the laminar flow, and if L is greater than the length at which transition takes place for a turbulent flow. Okay. So, let us look at all of those first. Okay. First one is transition. Okay. Okay. Rho V free stream transition length by mu, this is 5 into 10 power 5. Okay. That is the condition for transition. Recall that we have laminar flow up to a particular value, and beyond that there is a turbulent flow. Okay. And in the turbulent flow you have turbulent eddies, and transition takes place when this Reynolds number, transition RE, rho VFS times LT by mu is equal to 5 into 10 power 5 for this particular case. Okay. So, we substitute the values 1.25 kg per meter cubed is the density into 2 meters per second into LT divided by 1.8 into 10 power minus 5. Kg per meter per second is equal to 5 into 10 power 5. Okay. So, you can easily verify that LT is equal to 5 into 10 power 5 into 1.8 into 10 power minus 5, okay, divided by and you can do this calculation quite easily, and you will get this distance as 3.6 meters. Okay. So, the transition from laminar to turbulent flow takes place when the downstream distance is 3.6 meters. What is the boundary layer thickness at this location? Okay. So, let us examine that. Okay. Okay. We know that delta 0.99, okay, is going to be equal to Rex into x. Okay. In this case, x is the distance at which the transition takes place, that is LT. Okay. And Rex is the Reynolds number at which transition takes place, which is 5 into 10 power 5. Okay. Going to be 5 into 10 power 5. Sorry, I am sorry. X into Rex power minus half. Okay. Note that delta 0.99 by x is equal to Reynolds number power minus half. Okay. So, delta of 0.99 is x into Rex power minus half. Okay. At the point at which transition takes place, this is equal to okay, I made a factor of 4.99 here. delta 0.99 by x is equal to 4.99 REx power minus half. Okay. So, delta 0.99 is equal to 4.99 into x into Rex power minus half, which is 4.99 into LT, the length at which transition is taking place, into the Reynolds number. Transition takes place at 5 into 10 power minus 5 power minus half, okay, 10 power plus 5 power minus half. Transition takes place at Re is equal to 10 power 5 into 10 power 5, okay, power minus half. Okay. So, this will be equal to 4.99 into 3.6 meters into 5 into 10 power 5 whole power minus half. Okay. And if you do this calculation, you will get about 2.5 into 10 power minus 2 meters. Okay. This basically gives you the distance to which momentum has diffused from the surface as the flow is convecting it downstream, okay, in the flow past a flat plate. And you can see that this delta 0.99 is about 2.5 centimeters. So, when you have gone about 3.6 meters downstream, the momentum has penetrated only about 2.5 centimeters away from the surface. Okay. So, at a distance of about 3.6 meters in this case, this thickness is only about 2.5 centimeters. Okay. So, the effect of momentum diffusion is rested very close to the surface. Okay. Now, we can ask what is the drag force. Okay. For the laminar flow, Cf, which is equal to Fd by L into W. Okay. This is equal to 1.328 Re L power minus half, okay, which is 1.328 into mu power half. Reynolds number is rho Vfs into L by mu. So, we just have minus half of that, which is rho power half Vfs power half into L power half, okay, which means that the drag force per unit width perpendicular to the flow plane, okay, the drag force per unit width perpendicular to the flow plane is equal to 1.328 into L power half mu f power half by rho power half Vfs power half. And if you put in the numbers and do the calculation, you will get the result as 8.9 into 10 power minus 3, okay, L power half newtons per meter, force per unit length perpendicular to the per unit width perpendicular to the flow. So, therefore, the drag force increases proportional to the length of the plate to the half power in a laminar flow. Okay. In a laminar flow. Similarly, you can use the correlation for a turbulent flow. This is equal to Ft by Lw, okay, which is equal to 0.074 Re power minus 1 by 5 now. Okay, for a turbulent flow, recall the correlation was Cf is equal to 0.074 Re power minus 1/5. Okay, it's equal to 0.074. Mu power 1 by 5 by V free stream power 1 by 5 into L power 1 by 5. Okay. So, therefore, the drag force per unit width perpendicular is equal to L power 4 by 5 which is equal to 1.73 into 10 power minus 2 L power 4 by 5, okay, newtons per meter. Therefore, the drag force increases proportional to L power half for the laminar flow and proportional to L power 4 by 5 for the turbulent flow. So, this is a short discussion on the momentum transfer in the flow past a flat plate. We have covered the pipe flow, internal flow in the last lecture. This is the flow past a flat plate, and next lecture we will look at flow around objects. We will continue this in the next lecture. I will see you then.